So last time, let's pulsing a little bit. Last time we were talking about the wave equation. And this is calculus, essentially, equation. This is a simplified description of it. There's the H is the Hamiltonian, and psi is the wave equation. And it describes the electron as a standing wave. We're not really get into the equation, but you know, if it the psi function kind of like a sine wave, looks like this, and then when we square the wave function, then you get what we call a probability distribution. And then that gets turned into an orbital. And so this is a lot of ugly physics that we don't really want to get into, but we can actually talk about the results of so one of the results is there are 4 quantum numbers. And these basically describe where an electron can be. And the first one is called the principal quantum number. And it's given the character n. And n is equal to the size of an orbital. It's also equal to the energy level. And it's always a whole integer. It's a positive integer. Does anyone remember what an integer is? So it starts at 1 and it can go up to infinity, right, in integer form. Yeah. And so the n quantum number, n corresponds to the same n in the Bohr model. They're very similar ideas. So in the Bohr model, we had these places, these concentric spheres where an electron could be, and the closest to the nucleus would be, let's just make this whole thing the nucleus, 1, 2, 3, and 4, and so on. And so these values are equal to n. So as n gets bigger, we get a bigger orbital. The electron gets further away from the nucleus. So n1, low energy, stable, close to the nucleus. Okay, when n gets larger, then it becomes higher in energy. It becomes unstable and farther from the nucleus. So that's n. The next quantum number, the second quantum number, it's called the angular momentum number. And that's just because it involves angular momentum of the electron around a nucleus, and that's from physics. But it's given the character L, lowercase l, and it equals the shape of an orbital. And it's also referred to as the sublevel. So within these energy levels, 1, 2, 3, and 4, there are sublevels. Especially when you get further away from the nucleus. There's different places an electron can be. The L has values. It can go from n-1, n-2, in descending order down to as low as 0. And so L has different values based on what n is. If n is equal to 1, then L can only be equal to 0. If n is equal to 2, then 2 minus 1, L could be equal to 1, or L could be equal to 0. The L values give us orbital shapes. When an L value is 0, that's referred to as let's see, the name of the orbital and a drawing. That's an s orbital, and the drawing is a spherical shape. So that was the one I think we left off with that one last time. When L is 1, that's referred to as a p orbital, and it has kind of a two-lobe shape. When L equals 2, that's a d orbital, and that actually typically has 4 lobes, like that. And then technically L can go up higher and higher, but in terms of occupied atoms, we only go up to L equals 3, and that's what we call an f orbital. And that one it's kind of hard to draw, but it would have 8 lobes. So I guess 4 up top, kind of like yaw, and then 4 down below. All right, let's just say 8 lobes because it's hard to draw. All right, but that's the idea. Okay, so that's the second quantum number is L, and it's based on n. It's restricted based on what n is. So in my energy level, so basically if I'm in the first energy level, I can only have an s orbital. If I'm in the second energy level, I can have an s or a p orbital. We're going to see that's a pattern that comes about later. Let's continue. Oh, good, we have 21 now. All right, so the third quantum number is m sub L. It's called the magnetic quantum number. And m sub L is equal to the orientation of an orbital. M sub L also determines the number of orbitals that you can have in a sublevel. And then m sub L is, let's put it this way, it's based on L, based on the second quantum number. And m sub L can go from positive L to L minus 1, down to 0, and then up to as high as negative L. So we give an example. When L equals 1, then m sub L can be 1, 0, or minus 1. So in the L of 1 is a p sublevel. So in the p sublevel, there's 3 orientations. There's 3 different, I can have, that represents 3 orbitals. that I can have. So let's make one, let's call this the px. It's on the x-axis. And this one, let's call this one the py. The py, and it's on the y-axis. And the pz actually would be coming straight out of the paper. So I'm actually going to represent it at an angle. But imagine it coming straight out of the paper, like we'd have a 3-coordinate system. And that would be the pz. And so in a p sublevel, there's in a p, when L equals 1, in a p, I can have 3 orbitals. And technically, they all all 3 of these center on the nucleus. So technically, there's my x, there's my y, and then my z again would be coming out of the plane of the board. When L equals 0 and s, what m sub L values can I have? Anybody? It's kind of a weird system we're learning, huh? So let's go back. So m sub L can go from positive L in L-1 form to 0 to negative L. So if L equals 0, then m sub L can only be 0, which means there's only one s orbital. Oops, sorry. Orbital per energy level. Right? There's only one orientation. Because it's spherical, the orientation rule does not apply to an s orbital. Let's try this again. Let's do a different L number. What about L equals 2 for a D sublevel? How many m sub L's can I have for that? This one.
You can do 2, 1.
Yep.
And 0.
0. And then I can also go negative, right? I can have negative 1 and
negative 2.
Negative 2. And that's the maximum. So that means there's 5 d orbitals. And there's actually 5 orientations. They're more complicated than the P system that's just X, Y, and Z. Let's do L equals 3. What if L equals 3 and I have an F sublevel? How many m sub L's can I have for that?
It's going to be 7,
7, right? Because it would go 3, 2, 1, 0, minus 1, minus 2, minus 3. So there's 7 f orbitals. If we were, oh, by the way, after 3, I mean, technically that's the last filled orbital, but you can have higher values. So L equals 4, and after F, they just go alphabetical. This would be G, and L equals 5 would be H, but we never fill those. So G would have 9 orbitals, right? And H would have, with 5, would have 11, and so on. So I guess the basic idea, let's go back to the Bohr model. You remember these concentric rings. So as I get further away from so when I'm really close, when n equals 1, I can only have an s. There's only so many electrons that can fit there. There's too much repulsion. But when I get further out here, then I can have many different orbitals. There's many sublevels. There's many spaces the electron can be in. I'll bring the other there's a 4th quantum number I'll bring later. But actually, with the first 3, we can actually, there's a pattern. So in terms of energy, the lowest, so let's have n. So when n equals 1 is the lowest in energy, then I can only have a 1s. That is when n equals 1, L equals 0. That's all I get. I get 1 orbital. When I get to the second energy level, now I can have an s. I'm going to call it the 2s, second energy level, s sublevel. But I can also have a 2p. And how many p orbitals were there? So the 2p, remember there's a px and a py and a pz. So when n equals 2, then L can equal 0, which is this case, 2s, or L can equal 1, which is this case. And if L equals 1, then M sub L, there's -1, 0, +1, right? There's 3 p orbitals, right? Okay, let's continue. So if we get to the third energy level, then n equals 3, I can have a 3s and a 3p, and there's 3 of them. And then I can also have a 3d, and there's 5 of those. Remember that the -2, -1, 0, 1, and 2. And so there's kind of this pattern. Okay. So there's some quantum rules. Let me add to this. I may come back to this later. It's actually the fourth quantum number was actually found later. And this one's referred to as the magnetic spin number. And it's given the character m sub s. And there's actually only, so this fourth quantum number was found later. It wasn't, the other ones came directly from the Schrodinger equation. But this one was actually found by experiment. M sub s has only 2 values, +1/2 and -1/2. And these are basically electron spins. So an electron has a negative charge and it's spinning. And so when it's spinning, the electric field is spinning with it. And then there's a magnetic field. I'll call it B, because the physicists call it B. There's a magnetic field. So because when electric, magnetic. Electromagnetism is a single property, and anytime there's an electric vector, there's always a magnetic vector that's perpendicular to it. And so electrons, let me put this up again. Electrons around an atom are referred to as spin up, and they usually show this as a half-state arrow going upwards, or spin down. And spin down would be a half-staved arrow going down. The Pauli exclusion principle. So let's call this rule number 1, if you want. Right? The Pauli exclusion principle, named after a physicist named Dr. Wolfgang Pauli. And this states that in an orbital, you can have a maximum of 2 electrons, and those 2 electrons have to be spin up and spin down. So the idea is, so let's imagine an orbital. Let's just say an s orbital for sake of argument. We could imagine a p or a d or whatever. But in this orbital, if I'm going to force the 2 electrons, what happens, by the way, when I try to get electrons close to each other if they have the same charge? You guys remember like charges? What did like charges do?
They bounce away.
They like to repel. So if I'm going to force these 2 electrons into an orbital, their electric fields are going to repel no matter what. So the best thing we can do is have their magnetic fields attract, right? So the electric fields can't repel. Electric field repel, magnetic field better attract if I'm going to force them so close to be so close to each other. Okay, so that's the Pauli exclusion principle. There's some other rules. Let's continue. The next rule is the Auf Bau Principle. The Auf Bau Principle is literally a German word. Aufbau means literally fill up. It makes me think of Hofbrau, right? Or you go to a Hofbrau and you fill up on beer and sausage, I guess, or whatever. Anyway, so the Auf Bau Principle states that there's an order of filling electrons around an atom. And so basically you put electrons in the lowest energy orbitals first, comma, until full, right? And how many electrons can I have in an orbital?
2.
I can only have 2. So I'm gonna whatever that lowest energy orbital is, I'm gonna put 1 electron, 2, and then once it's full, then I'm gonna put them in the next higher. Then put in the next higher. All right. There's for the Auf Bau Principle, there's kind of a general guideline, but then there's a more specific rule. It's kind of a weird rule. So in general, the first energy level is lower than the second, is lower than the third, is lower than the fourth, and so on. So you'd want to put electrons here first, right? You'd want to put them in the first energy level, and then if you remember those concentric rings, when the first energy level is closer to the nucleus, that's lower in energy. So I'm going to put electrons here until full, and then I'm going to fill up the second, then I'm going to fill up the third, and so on. Okay. Also, s orbital in general is lower than a p orbital, is lower than a d orbital, is lower than an f. So in general, I'm going to put electrons in an s orbital until full, and then I'm going to start filling up the p orbital of the same energy level, and then the d and the f if they exist in that energy level. So there's kind of a caveat for this. This is cantankerous, but I'm going to write it. Some lower sublevels of higher energy levels are lower in energy than higher sublevels of lower energy levels. Oh my God, what did he just say? So let me give an example. Not all of them are that way, but some are. So the example is that a 4s orbital is lower than a 3d. So this is a lower sublevel. S is lower than a D. It's a lower sublevel of a higher energy level. The fourth energy level is higher than the third, right?
So when it's like this, we're following the SPDF. Is that
so
what that is?
There's two ways to, so this caveat comes about, and there's two ways to deal with it. One, there's a mnemonic. I could teach you if you want it. I'm not as excited about the mnemonic, but it's in the periodic table. So the periodic table is actually the chart. It will show me the order of filling once I learn how to use the periodic table. So for the mnemonic, I think it's got a U in it. Mnemonic. Okay, for the mnemonic, basically, you create all the orbitals there are in each energy level. It's kind of this is a longer mnemonic than some of the ones we've learned before, like 3, 2, 1. You create all the orbitals there are in each energy level, and you fill with arrows diagonal down and left. So here's the mnemonic. So there's the first energy level, the second, the third, the fourth, the fifth, the sixth, the seventh. Technically, energy levels keep going, but in the occupied atoms that we see on the periodic table, we actually only go up to 7. Okay, so in the first energy level, what orbitals can I have?
We can have S.
Yeah, all we can have is a 1s, because when n equals 1, L can only equal 0. That's the only choice, right?
Yeah.
Okay, in the second energy level, I can have a 2s and a 2p, yeah?
Mm-hmm.
Okay, because L can be 0 or 1. In the third energy level, I can have an S, I can have a P, and I can have a D. By the way, this is kind of nice to point out. There is no such thing as a 1. So let me, on the side, there is no 1p. There is no 2d orbital. They don't exist. The mathematics that created these wave functions does not support those. They're said to be quantum mechanically not allowed. Okay, they won't happen in the physics equations. Okay, so in the third energy level, we get 3 sublevels. In the fourth energy level, guess how many sublevels we get?
4.
4. We get an S, 4S, and a 4P, and a 4D, and what else?
4F.
A 4F. Good. So following this pattern in the fifth energy level, what could I have?
A 5S, a 5P, 5D, 5F.
Technically, you could also have a 5G, but it never gets filled. So I'm going to put it in red. Is that okay?
Mm-hmm.
But quantum mechanically, a 5G orbital is allowed if you're in the fifth energy level. If you're in the fifth energy level, if you're that far away from the nucleus, you can have 5 sublevels. Okay, then the sixth energy level, I'm just going to do this quicker now. 6S, 6P, 6D, 6F. Oh, there is no 6F. Let's put it in red. 6F, 6G, 6H. So again, after F, the new orbitals that are created are just alphabetical. And then in the seventh, there's a 7s and a 7p. That's actually the end of the periodic table with element 118, the newest element they ever found. But technically, you could have a 7d, a 7f, a 7g, a 7h, and even a 7i. So then the order of filling is you go arrows diagonal down and to the left. You start up here, and so first I'm going to fill the 1s. Then I'm going to fill the 2s. So far, so good, right? Then I'm going to fill the 2p. What's after the 2p?
3S.
The 3s. So far the order is the normal order you would normally expect. Then I'm going to fill the 3p. What's after the 3p?
4S.
Yeah, so the 4s is out of sequence, right? So if you were just to go in energy level, I'd go 1s, 2s, 2p, 3s, 3p, 3d, 4s. But actually, quantum mechanically, when they do the physics calculations, the 4s is lower in energy than the 3d, so it gets filled first. So I circled it because it's out of sequence. And then I'd fill the 3d, and then what? Then the 4p, right? So the 4p is out of sequence, right? Because I'd want to fill the rest of the fourth energy level. Well, okay, I guess not. Maybe that one's not out of sequence, but the 5s is for sure. And then I go back and fill the 4d, but before doing the 4f, I'm going to do the 5p. And also before I do the 4f, I'm also going to fill the 6s. So this is another thing that's predicted. When I get further down in energy levels, it gets more mixed up. Here I'm filling the 6s, I'm filling the 6th energy level before I even finish the 4th energy level. How interesting, okay? So that's a mnemonic you can use. And so then after that, we fill the 4f, then the 5d, then the 6p, then the 7s, and then the 5f, and then the 6d, and then the 7p. And that's the end of the periodic table. So these other ones, let's never filled.